Hi, my name is Pablo Galindo.
And my name is Łukasz Langa.
And this is the Core.py podcast, a new podcast where we discuss the internals of CPython and other adventures in making a new version of your favorite programming language. Today, we'll be talking about the heart of Python and the bit that makes the interpreter an interpreter, which in CPython is called ceval.c.
Right. When I was looking at the current state of ceval.c, I was a bit scared of trying to explain it from the get-go. When I started contributing to Python, when I started using Python, things were simpler. So how about let's go back to this historical part of Python, which still to an extent is the same, but the source code for it is much easier to reason about. The easiest way to understand where we are now will be to look at the simplified case first. So let's go back to Python 2.6. You will probably have trouble compiling that version on modern Macs and Linux boxes, but you can use the CentOS Docker image with the tag CentOS6 if you're curious to try it out yourself. To be clear, I don't expect you to be running Python 2.6 right now when listening.
Yeah.
More importantly, you can find the code for what we'll be talking about under the 2.6 tag in the python/cpython repository on GitHub. And I chose 2.6 specifically because it's the last version before any optimizations that make it hard to see how Python evaluates your code. If you are really curious, you can look up the 0.9.8 tag on GitHub and look there too. But at this point, this is too different from what we have today.
You're painting this as if listeners will have a lot of trouble running it, which may be true. But I was going to add, unless they probably work at certain financial institutions, when probably they can just look at their normal repository and check how the code works.
Cool. In my particular case, I tried to compile it myself, like neither PyEnv or my attempts to do it on my own succeeded because of expectations of way older libraries to be there on the operating system, and then some macOS shenanigans being different back in the day compared to what we're doing now. So I just gave up and decided hey, probably there is some Red Hat or CentOS still. CentOS maybe not a thing these days as I remember it, but CentOS 6 turns out you can just start the Docker image very quickly, and there you go. There's Python 2.6. And on GitHub, the tag is forever, so you can go ahead and actually find the ceval.c file there in the Python folder in our repository.
So this file contains basically the core of the interpreter. And before we understand what's going on here, we need to understand basically how Python runs programs. And, this can change from different implementations, but most implementations of Python, and in particular CPython, uses a stack virtual machine. And this is because, when you are running programs on your computer, there are different models of how your CPU can execute code. And when you are talking about dynamic languages, we normally abstract CPUs in software, so we can decide how to run different instructions. And it turns out that most programming languages fit the stack model very well. This is just a way to execute programs. There are others like register machines when there is different registers that can hold data. But CPython uses a stack model, and this is what ceval.c implements. It's the stack evaluator.
Right. For example, if you have nested function calls, in other words, you use a function call as an argument to another function, what Python needs to do is it will call the function that is the argument first. It will hold on to the return value of that function and pass it on as an argument to a call to the outer one.
Right. So the idea here is that when you are executing these functions, there will be some data structure, which is a stack, and the results will be pushed to the stack, and when they will be finished, they will be popped from the stack, right? So the idea is that we store the data internally in this particular data structure, even if you never see this when you run Python programs.
Right. So to see how this works, let's consider a simple code fragment, lambda : x + 1. So it's an expression that creates an anonymous function, right? This is what the lambda keyword says.
Right.
You can assign this expression to a variable or use it inside a function call as an argument that is a callable. So what does the function in the expression do? Well, it takes a non-local variable x, adds 1 to it, and returns the result. But when you write lambda colon x plus 1, you're not adding 1 to x yet, right? You're creating a function, a kind of code object, which is a template for code execution that will happen at some other time. To see how this code object looks like internally, you can disassemble it using the dis, spelled D-I-S, standard library. So import dis from dis and call it with our little lambda expression as the single argument. In other words, you will say dis open paren lambda colon x plus 1 close paren. So when you see this in a REPL, it will return a bunch of opcodes for you. Some uppercase names like load global, load const, binary add, return value. In other words, these are identifiers for granular operations that the stack VM can perform. In our case, there will be 4 of them. First, there's load global x. So the code first loads the global onto the stack, and then load const 1. So a constant, it needs to find it somewhere, load it and put it onto the stack. Then we have this binary add operation that uses what we already have on the stack as arguments. So it removes those 2 arguments from the stack and puts the result of the operation back onto the stack. And then we have the return value opcode that just returns the value on top of the stack. That's what the Lambda is doing.
Right. One detail here, just for our listeners that may not be familiar with the term, sometimes we say that this is a stack VM. VM here stands for virtual machine. And this is just referring to the fact that we are abstracting like how the CPU works. So we are not talking about, the VMs that you will install to install other operative systems, as when you need to install Linux on Windows or Windows on Linux or whatever. We are talking about here, when we say VM, we talk about like the abstraction of a CPU or like lower level hardware on software, which is what CPython is implementing here.
Yeah, totally.
So these are opcodes, and unfortunately we are not going to go into all possible opcodes today because this podcast is really long and we don't want to take you 6 hours, and these opcodes change between different versions of Python. But what is important to understand here is where these opcodes come from. And what happens here is that when you write your program, you write a text file with your like Python source code. So CPython and Python in general will basically grab that source code and using the parser and the bytecode compiler will transform the text that is your source to the different bytecodes, right? So different functions will create different bytecodes. And the important here is that these bytecodes are just templates for code executions.
Right.
This means that it's just instructions that the interpreter needs to do, but there is the other ingredient that we need here to actually do something, which is data, right? You need to know, talking about what Gukesh was talking before, if you are going to add 2 things together, well, sure, the opcode says, binary add, but you need to know what things are you actually adding together, because you could be adding integers, or you could be adding strings, or maybe you're adding an integer and strings and that will blow up, right? So when we introduce the values of those variables, Python needs to do something with that data and that bytecode, which is what we call evaluation. And basically, evaluation is just bringing the 2 together. And the way to think about this is that when you're in a function, for instance, but there are other areas of execution, but functions are the simpler ones. Every function has its own local scope and local variables and arguments. And the idea is that, and more complicated things like you can have non-locals, and like class scope is even weirder. But the idea is that CPython will grab this with this data together with the opcode, and then will start executing this. And because CPython needs to know in every instant what is the status of like what instruction is being executed and what are the values of the local variables, because obviously as you run your function, those can change. This state needs to be stored somewhere, and we call this thing execution frame. So when we're talking about frames, you need to think about basically what the function is doing at some moment, right? So what instruction is being executed, but also what is the value of all the data. And frames contain more things than just these 2 things. But for what we need to discuss here, this is the first thing that you need to know. And evaluating a frame is unsurprisingly called frame evaluation.
Right. So when I first started looking into programming languages still at university, the thing that I couldn't quite understand was why wouldn't the data that we need with this code object be just stored on the code object?
Yeah.
But later I understood that obviously the same function can be in some state of execution multiple times at the same time in an interpreter.
Right.
Either you have multiple threads, or you might have a recursive function, so a function that calls itself. And in this case, there's going to be the same function having different data at the same time, which is why we have separate frame objects for this. So to evaluate the frames, we're going to actually use a single big loop that literally goes through all the opcodes that we need to deal with and executes them one by one. So to see it now, it would be a little complicated, but to see it in Python 2.6.9, you can go to the Python directory, open the file called ceval.c, and in line 561, you will actually see the function pyeval, eval frame, ex.
What does this do?
So that's the function that does all the evaluation. And in it, there is going to be a bunch of defines, and at line 830, you literally have this forever loop. It's a for loop with no arguments, so just 2 semicolons inside. And this loop checks a bunch of things first. And at line 971, we literally have a big switch statement that implements what each opcode does. Some are simple, like load const that I already covered. That is just a lookup of the consts that are on the code object that encrypts the result and pushes it back to the stack.
Right.
Other opcodes like binary add are surprisingly rich because they implement several combinations of argument types and work around possible error conditions. That tells us that not every opcode is on the same level of complexity. Some are just a few native instructions and some are very complex. So in line 1690, you have an even more interesting detail because we at some point reached so many case instructions in the switch that some of the compilers of the time were not able to handle the complexity of the switch statement. So we had to have a nested switch statement in the default case, just so that older compilers could still compile Python. We couldn't handle 112 cases that we had in that switch statement in Python 2.6. But coming back to frame evaluation, we already mentioned that programming languages fit the stack model well, and this is true for frames as well. Code execution, in the grand scheme of things, is function calls that contain other function calls that contain other function calls. So the innermost function always returns first, unless we're talking coroutines, but let's not go there now. So the innermost function always returns first, and then the one that called it, and then the one that called the other one. So they form a stack. It's not the same stack that we talked about with the stack VM, but it is a stack.
Right.
Where I'm going with this here is that for every Python function call in the olden days of Python 2.6, we had a single C call as well to pyeval, eval frame x. So it was very simple to see in C debuggers and profilers and so on that for every call that you had in your Python source code, there was an equivalent C level call to pyeval, eval frame x. And right, like if you are now scrolling through this 2.6 life, you might think, oh, actually, not so bad. And if you're not because you're commuting or whatnot, you just have to believe us that, it wasn't extremely hard to understand what the core of the interpreter was. But that was then.
Right. And also, it's interesting to notice that we said the word stack, probably referring to many different things, because there is plenty of stacks here. And just to clarify, so there is the data stack that the interpreter uses to push the arguments of the functions. When you are adding numbers, you need to push first the two things that you are adding to the stack, and then you take them to add them, and then you push the result. So that's one stack. The stack that Łukasz just mentioned is the function stack. That is what you see when you see traceback. That is the Python function stack. And then there's the C function stack, which, because this just happens that CPython is implemented in C, obviously that's the C of CPython, and that's a different thing. And there is some tension between the two, because you could theoretically never exhaust the Python stack. You could imagine a world when you can call functions and functions and functions and you never finish, but the C stack has a limit, and that's what you get, when you exhaust the C stack, you get a stack overflow. And we will see how we handle those cases to, not crash Python later. But just if you have reached this point of the podcast and then you are like, your head is spinning out, like, what does a stack even mean? There is all these stacks here. So when we say it's a stack machine, well, it's like a stack machine along another stack machine, executing on top of another one. So it's a very interesting thing.
Yeah, it's a stack of stacks, essentially.
Yeah, exactly, like nested stacks, right?
Right.
That fits very well the stack model as well.
Yeah, like the frame evaluation executes opcodes. You probably already found out at some point in your usage of Python that PYC files of one version will not work with another version of Python. And this is because a different version of Python will use a different set of opcodes. And the reason why is that there are plenty of new opcodes for new features. So for example, in Python 3.10, we added match class, match mapping, match sequence, and match keys to support pattern matching. Some opcodes were added as specialized, more efficient variants of common operations. And one interesting example is load method that was added in Python 3.7. And after Python gained the full-blown specializing interpreter, this opcode was again removed in Python 3.12, because now we have a more generic way to achieve this optimization without having to use a separate opcode.
Right. And talking about optimizations, one of the things that made the interpreter much faster, but actually complicated the code quite a lot, it was the addition of computed gotos. This is also called, if you're a PhD student, you probably will call this threaded code, because it's a much more confusing way to refer to the whole thing. But everybody in industry calls this computed gotos. And the first time you see this is quite surprising, because this is not a standard C, actually. This is not in the C standard. This is not something that you can actually do with C. But turns out that most compilers actually support this, with the exception of the Microsoft compiler. We are looking at you, buddy. Go to the future. And but the idea here is that because we have basically this big for loop that is executing different opcodes, every time you execute one, you need to basically see the opcode that you're looking, go to this ginormous switch statement that Gukesh mentioned before, and then you need to jump to the particular case that is handling that opcode, right? And then another iteration of the loop will do the same and the same and the same. Well, this is already good, because that's what you need to do. But turns out that if you have certain opcodes working together, there are certain inefficiencies there. For instance, you will see that some opcodes will appear always in pairs, right, or one after the other quite a lot. And modern CPUs, they are very good at predicting what will happen when you execute one instruction, what will happen next, right? And then we have all these new technologies that will be able to try to predict what will happen and pre-execute it in that case. But the problem is that we are talking about at the level of opcodes, and the machine is only looking at a stream of instructions, and every single instruction will need to jump to the next like the beginning of the switch statement to jump to the next instruction, which means that from that point, when the switch happens, CPUs will have a really hard time predicting what is the next opcode that will execute, because the switching point happens at the beginning, right? You read the switch, you read the opcode, and then you jump somewhere in the hundreds of opcodes that we have.
Right.
But normally, if you have a load const, there are only a very certain amount of opcodes that can follow. And this is where these computed gotos appear here. And the idea here is that you don't jump to the beginning of the loop and then you hit the switch statement. The idea is that you jump directly to the next instructions. Obviously, you need to check that the next instruction is the one that you are predicting that will happen. But if that's the case, you will skip the switch and you will jump directly to where the instruction is, and you will continue executing there directly. It's like as if you copy-pasted the code of the next instruction after the one in the previous instruction, right? And that is much more efficient, because you skip the jump to the beginning, so you skip a bunch of instructions from the handling of the jump table. But also you can leverage the branch predictor of your CPUs, which is what is going to make your Python much faster. because it will start seeing that, after these load cons, then these other instructions will appear, and it will be able to start mapping what instructions are following what other instructions, and it will start pre-executing that code before the CPU actually hits it, and that will speed up quite a lot the code execution. And this, when you see this actually happening, because these are gotos, and gotos needs a label, right? You normally write this as goto some label, and then the label is specified as my label colon, right? And that's where the jump will happen. You will see that the syntax is a bit funky, because you will take the address of a label. That is something that is extremely super weird in C, and actually that has the type of that is a void star. And when you jump to the actual label, you will dereference the pointer where you're storing the label. And that's the only case in C that I have seen that you can dereference avoid the star pointer, because normally you cannot dereference avoid the star because you don't know the type. This is the only case when it will look like if you are dereferencing avoid the star pointer, which is quite cool. But it's not compliant C, it's just a compiler extension. But everybody uses it these days because it's much more efficient.
Right. It's quite cool. But what it means is there is no longer a very easy to read switch statement. So when we added this in Python 2.7 and at the same time in Python 3.1, this got Python 25% faster for this particular use case. So that's great. But it made this code a little less clear to read, which is why we went back all the way to Python 2.6 to introduce frame evaluation, because at this point, this magic was not happening yet. And speaking of speeding things up, a very popular demand from Python users is for Python to have a JIT.
Right.
And what does that mean? What that would mean is replacing what we're talking about right now, which is frame evaluation by interpreting opcodes, with first compiling and then executing pieces of machine code directly that operate on your data.
Right.
That would obviously be much faster, and because we know that there are Python interpreters that do support just-in-time compilation, it would make sense to have this functionality in CPython as well.
Right.
And in Python 3.6, Brett Cannon landed PEP 523 that allowed certain tools to plug into the frame evaluation API and essentially replace the default interpreted evaluation with something else.
Right.
So in other words, there is now a function pointer in PyInterpreter state that allows replacing PyEval eval frame default with some custom function that might execute more than just a single opcode. It might execute more than a single frame. It might just keep executing for a while.
Right.
So there is one experimental JIT for Python 3.10 using this API called Pigeon that was started by Brett Cannon and continued by Anthony Shaw. So this project uses the .NET Core CLR JIT with Python. Depending on the benchmark, it shows minor improvements all the way to over 2x improvements, but it isn't a major improvement for generic Python code. One other JIT implementing PEP 523, this time for Python 3.8, is Piston Light, and that shows 25% improvement in Py performance over
this
regular
is
Python 3.8.
The one associated with the Piston project, right?
Exactly, yes. So Piston is a specific fork of CPython that is essentially replacing the frame evaluation code with something else. And Piston Light is a form of this interpreter as an extension module that uses the PEP 523 API to plug into regular Python interpreters that you're going to find on your operating system or some other way that you're, downloading Python. Right. So for specific use cases, this kind of API can be more effective. For example, Torch Inductor, the default backend that compiles graphs into machine code for unmodified PyTorch programs, uses PEP 523 to achieve speedups of over 3x.
Wow.
And it's using this by fusing sequential operations to avoid excessive reads and writes, as well as by doing out-of-order execution, something that the C compiler loves to do, and automatic work placement that's hardware-dependent. But in general, it turns out that having a JIT that compiles at the boundary of a function call or a method call isn't very effective. So PyPy, for example, is different. it can compile long chains of instructions called traces that go outside of a single method call. So the faster Python team now recognizes this and is working on a new pluggable optimizer API to replace PEP 523. It's currently experimental. It allows registering an optimizer with PyOnstable underscore set optimizer for now. It works with one or many executors that can switch execution between them, including even tail call optimization, which I found really interesting. So, however, a surprising use case appeared for PEP 523, which actually makes it still alive and kicking. It's currently used for debuggers. Like the PyCharm debugger uses this API instead of the traditional sys.setTrace API. And as Liza Shashkova reported in her PyCon 2017 talk, this was over 10 times faster in the worst case and up to 80 times faster in the best case, making the debugger a way better experience than before.
Well, this is one thing that always scares me about people using PEP 523 is that this interface is extremely unstable in the sense that I think even in the PEP we mentioned that the API can change from any Python version to the next. And in Python 3.10 actually, because we change all these optimization regarding frames and we make them faster, now the actual argument to the function that you need to provide in PEP 523 is technically opaque because it's one of these frame, interpreted frames that are not supposed to be in the public API, which is kind of weird because you need to provide a function that receives an argument that you cannot inspect. But obviously, if you are going to implement one of these, alternative, interpreter evaluators, you obviously need to inspect the frame because that's where the data is, right?
Right.
And so I'm very interested to see where all these use cases go, or like what we're going to do in CPython if we are going to, have the two APIs work at the same time and be compatible with each other, or we are going to force everyone to move to PyOnstable set optimizer in the future if that works to be turns to be better. It's an interesting certain case for sure. But talking about like improvements, one very cool thing that happened on Python 3.12, that is not very visible, but this is going to help us a lot in Python 3.13 when we release it later next year, is that Widow created a new DSL basically to define the instruction semantics for every opcode. And this is because like ceval.c, apart from being this big for loop with the big switch statement inside, it has a bunch of other things, right? And all of them are extremely entangled. This file is super big. It's one of the biggest C files that we have in CPython that is mostly handwritten. And the idea is that it deals with evaluation, but it also deals with like error handling, like what happens if there is an exception. Tracing, for instance, coverage used to it still uses this, right? Like, because they have not moved to the new cool stuff. It also deals with instrumentation now, using the new implementations of the coverage and instrumentation that Mark did, that Gukas was using for the coverage stuff. And it uses a bunch of other implementation details. So the idea is that we have this domain-specific language, that's what DSL is, that basically describes all the semantics of the different opcodes. And then there is this program that reads this description and it generates most of ceval.c. You could argue that we already kind of have a DSL in ceval.c because if you look at it and you look at how these instructions were written, even in all Python, like Python 2.6, which I like to call legacy Python now, I think we are enabled to do. You will see that there is a bunch of C macros that do a bunch of things, like for instance, stop, pop, and push. And those are basically just expanded to do some operations with the data stack. Like I want to push this value on the stack and I want to pop from the stack and get it somewhere. So you could argue that there is already some auto-generated code there via the C macros, but this is a whole new thing. The idea here is that there is an entire specification that auto-generates a lot of ceval.c. And this means that now we don't have anymore a switch statement because now there is all these different things. And the key here is that this is not just for maintenance purposes, because you could say, well, that's kind of cool that you write like descriptions and then there is machine code that generates things. Obviously, that makes easier to change stuff and less error prone, because if it can be auto-generated, it means that there is less mistakes that you do. But the idea is that the reason we did this, and the reason we did this, is to start allowing implementing what we call tier 2 interpreter. And a tier 2 interpreter is basically the same idea. So it's a loop with, conceptually at least, it's a loop with a switch inside. But this doesn't operate on opcodes, but what we call micro instructions or micro ops or uops, as is referred in CPython. And the whole idea is that a JIT compiler likes these instructions much better because they are more granular, right? Like as Gukas mentioned, there is instructions right now, bytecode instructions that are very small, like load const. That basically gets a value from the stack and put it somewhere. But like binary add is one of the big ones, and there are even bigger ones, right? Like the ones used to unwind exceptions or call functions or set up with statements. All of those can be quite big.
Right.
And they have a lot of complexity. So a JIT compiler will struggle optimizing around. And for instance, the first micro op that we implemented is for iter. And the idea is that when we have this copy and patch JIT compiler that we talked in the first episode that was presented by the Faster CPython team and by Brand in the Python core developer sprint of this year. And the idea is that this JIT compiler will be able to take a stream of these micro ops and then it will replace them by a single piece of efficient machine code that is composed by copying and pasting especially precompiled chunks. So the idea is that we'll have these templates written in C that we can auto-generate via this description, and then we will have a compiler that will compile this to very like native code that is going to be very efficient, because we use the native compiler to compile these things to native code, and then we will basically copy what the compiler produces and place it somewhere. Then we need to kind of recompose later, because if those functions that are compiled are calling some random function in the Python interpreter, like I don't know, by number add, obviously they don't know where this function is in the code segment, because that only will be known at linkage time, right? But the idea is that we will grab this with some holes that we call it, and then we will replace those holes, which are the addresses of these functions, at runtime once we know where these functions are. And even if you are very excited to hear about this, because you will say, wow, that's kind of cool, the JIT compiler is very important, because the tier 2 interpreter is actually doing a lot of stuff that is extra, and without the JIT compiler, this is actually not faster, it's actually slower. And as Brad mentioned in the Python core developer sprint, I think if I remember correctly, tier 2 interpreter is 5% slower. And with the super prototypey, drafty JIT compiler that he had, just to prove the point, this was 0% faster and 0% slower, because 5% of cost for the tier 2 interpreter and 5% gain for the JIT compiler, to a total of 0. But the idea here is that as we improve the JIT, because this was a super drafty version, this will start being a positive number, and hopefully a very big positive number.
Right. The tier 2 interpreter is still a work in progress, very much so. The interesting bit of this is the entire executor API is being developed at the same time. Those things are experimental, and so on and so on. So if you are looking inside Python 3.13 right now and try to understand what's going on in ceval.c right now, this will be pretty confusing and hard to understand, which is again why we started our story in Python 2.6, where, for example, binary add existed. These days we no longer have binary add, we have binary op.
Right.
And the actual operation is an argument to this opcode. So those things tend to change all the time. And one of the things that changed was this thing that I told you before about how it used to be that when you called a Python function, every time that meant we called a C function at the same time, which was used by many pieces of tooling for Python and C to look at the stack of calls and to be able to tell you that, oh, this function called this function called this function, and display you a nice traceback, for example, in GDB or in some sort of profiler that you ran against Python. So these days, for efficiency reasons, we grew a way to call Python functions from other Python functions without having a new C call to PyEval eval frame default. This turns out to be much faster, and by the way, the frame data that we're using for this isn't even a Python object anymore.
It's interpreter frames.
Right, but as a result, we are complicating lives of tools that rely on reading the stack of C calls to PyEval eval frame default. If you want to have a frame object in Python, there are still APIs for this, obviously, right? So you can still get this in your Python code. So how does this work? Well, Python will create those frame objects for you on demand, but only when you ask. If you don't ask for them, this is going to be now more efficient in a representation that uses less copying and is more memory dense.
Right, one of the, well, I wonder, by the way, who did this. And it's going to be even funnier once I reveal that I, had problems by my own patch in CPython. Well, I did this with Mark Shannon, just to be clear. It was not just me alone.
Very cool.
But one of the, important things that happen here, apart from making Python calls much faster, because you don't need to do all this pre-work of, preparing ceval.c to call PyEval eval frame default every single time. You can basically reuse it. Now the problem is that there are tools that will analyze the C stack, and it will try to reconstruct what Python calls were there. And this is very important because, for instance, imagine that you're running NumPy or any C extension and it crashes. You normally want a debugger or any tool to tell you where that crash happened, and normally you need to deal with the C stack there. And when you see the C stack, you're going to see that a bunch of functions that are being called, and from time to time you're going to see PyEval eval frame default again and again and again. And every time before, in the old times, as Gukesh mentioned, every time you see one of these PyEval eval frame default, that was a Python function that was running there. And all of these debuggers, including the GDB bindings that we have in CPython, in the CPython repo, but also things like PySpy or Memray or PyStack, those were able to basically grab the C stack with all those PyEval eval frame default calls and figure out what Python version was running on those calls there. So it will show you what is called a hybrid stack. So, a bunch of C functions, and then there is these Python functions, and then a bunch of other C functions, and so on and so forth. But now, after this change, one call to PyEval eval frame default can be assigned to an infinite number of Python functions. So there is not anymore a one-to-one relationship, which means that all these tools were broken in Python 3.11. And even to this day, PySpy, for instance, is not working for Python 3.11 plus, because they have not still, unfortunately, had time to fix this particular problem. So if you run it with native, it won't be able to merge the stack, because it will say that the stack are not matching because there are more Python function calls that C calls to PyEval eval frame default. And this is not an easy thing to fix. I had to fix this in on Memray as well, which is a profiler I maintain myself, which is poetic justice, right? So you make Python interpreter faster on one side, but then on the other side you need to just pay the price in blood in your own packages.
Right, yes. So there is definitely tension between making sure the default case of user executed code is efficient and allowing you to profile and debug what is going on inside a running process. One example of functionality that we used to have for this particular case is DTrace. So I added DTrace for Python 3.6, which essentially what that means is there is a bunch of probes inside the Python process that usually get compiled into just NOPs, operations that don't do anything on the CPU, but they have places that can be patched with some other code that, for example, reports that a line was executed or whatnot. And the way you do this is with enough privileges. So, for example, on Linux, you need to be root. On macOS, you also had to be root for a while. And these days, you cannot run DTrace at all unless you reboot your system, disable system integrity protection, and then only then you can run DTrace on another process.
And make some blood sacrifices, I suppose.
Yeah, so that's a blood sacrifice like every time the user wants to actually do this. So this essentially broke on the operating system layer at some point for macOS. So we weren't really testing this very thoroughly, honestly. And the reason why was that none of our automation for running tests is assuming that it will be running with root privileges. It's kind of scary if you're running a build bot that is going to run random pull requests, and it's going to be executed with administrator privileges. So we don't usually do that. And because of this, when the large changes to frame evaluation came, a bunch of those probes that were, for example, reporting whether a line was executed got broken. And that was back in the 3.11. And for 3.12, the situation got even more complicated. But at that time, Mark Shannon identified that what we really need is some way to instrument the Python process in a way that doesn't hinder performance by default. And the complication with probes that DTrace provides is that they are statically compiled into the binary in a way where the client that tells the process, okay, now we're going to replace your no-op with some operation that is going to actually do something interesting, it doesn't understand what Python is. It doesn't know what variables around that particular probe need to be queried and how to learn, for example, what line is being executed right now. So this form of probe is going to be very hard to implement. So instead, what we gained was PEP 669 with a replacement for most of the uses for sys.settrace and PEP 523 and DTrace. So this kind of instrumentation turned out to be pretty successful for some of those use cases, and we already see this. For example, the kind of test coverage gathering that I implemented using this functionality is essentially 10 times faster than what we had before. And, to some extent, it is even better because it actually finishes reliably and so on and so on. So this is pretty cool. But there are still holdouts of some old APIs, like sys.settrace is still necessary for all the libraries like coverage.py that need to work with older versions of Python as well. PEP 523 is an API that is extensively used, for example, by the torch inductor that I already talked about. So switching to a different API is not going to be very easy for existing users. So this is going to be still some sort of transitional period, especially with the new executor API coming. We'll see how that is going to look like. But there are very many ways to instrument a Python process. Some of them require you to build it in a special way. For example, if you build Python with PyDebug, one functionality that you get specifically for frame evaluation is the so-called low-level trace, or lltrace. This is something that allows you to get output of what bytecodes are being executed at a given point in time. And starting with Python 3.11, there's even a better way. Now you can build Python with --enable pystats to gather VM stats on super many things. Like, I knew about a bunch of those, but when I actually read the documentation for that option, I was essentially blown away how many details now are available. Like this sort of thing in 3.11 was already pretty rich, but what we have now is somewhat crazy. So you have like all stats about how many specializations were attempted, how many succeeded, failed, how many frame objects were created, how many Python calls were inlined. So we were talking about.
This is what the faster CPython team uses to optimize certain cases, and the reason is because like even if you execute a bunch of Python code, if the overhead is in the interpreter itself, like executing instructions, it's very difficult to know exactly what is the cost of executing those instructions. Like you want to know like what instructions are executed more than others, but like as you can imagine, like for instance, the time you spend in load fast is different from the time you spend in like setting with the statements and whatnot. And also like if you and in very complicated cases when the optimizer tries to optimize a certain instruction for using floats, but then you pass integers and then you pass floats again, and you are like in this dance of going back and forward. You want to identify that is the actual problem. And the moment all of those things start to work together, you need all this crazy data just to understand what's going on. And this is something that we execute in benchmarks as well, just to ensure that we understand why a benchmark is becoming faster if we make an optimization in the interpreter and not because something else changed.
Right. So we covered how ceval.c is used to actually interpret user code, but there are a bunch of other things that happen inside that important loop. So can we talk about that for a bit, Pablo?
ceval.c, even if it's complicated and it's full of all these things, there are quite a lot of other cool stuff that happen also on ceval.c. So one of the things is that we call the Eval breaker, and there is a lot of fun that happens here. So basically, the Eval breaker is this function that, it's technically not a function, it's just a piece of code that is in line in the, because every time you call a function in ceval.c now it's like 3 times slower or something like that. So everything is less in line in this enormous file. But the idea is that when you are executing bytecodes, so you are executing one and then the other and then the other, from time to time there is this code that runs. So evaluation stops, and then there is this special code that starts running where we call the Eval breaker, and it's called the Eval breaker because we are breaking evaluation just to do these things. And from time to time, this did like just a bunch of very simple things like checking signals, for instance, which is quite funny because signals have a very interesting set of behaviors that maybe we can talk later. But now, as I think we mentioned in the past podcast, one thing that we changed in Python 3.12 is that the garbage collector only runs on the Eval breaker. So before, the garbage collector, the cycle garbage collector had opportunity to run every time you allocate a Python object. So there is a bunch of we can maybe talk about this in some podcast episode, but there is a bunch of heuristics when the garbage collector can run, basically based on how many objects are alive and how many objects are in the different generations. But the idea is that every time you allocate any Python object, there is a chance for the garbage collector to run. And that's kind of problematic because when the garbage collector runs, it can execute arbitrary Python code, because when the garbage collector removes some objects or even call finalizers, those objects can have __del functions, which we call finalizers, it's not destructors, it's finalizers. And that can basically do whatever. Right? So basically, this means that every time you allocate a Python object, the state of the entire world in the next line can change. And this makes writing very specific code in ceval.c very, very complicated, because when you're dealing with exceptions or frames, the fact that an arbitrary number of Python calls can happen is really, really difficult to deal with. You can imagine, for instance, if you are allocating a new frame of execution and then suddenly the GC runs, you are entering ceval.c while you're in the middle of allocating a frame in ceval.c already from a different place, right? So you don't want that.
Right.
And that was the source of super complicated bugs that Bram Booker actually, very heroically helped us fix regarding different frames and the garbage collector running in the middle, which is, very confusing. So something that I changed in Python 3.12 is that the garbage collector doesn't run anymore on allocation, but it runs on the Eval breaker, which means that it can only run from time to time when the interpreter is executing bytecodes. And there is a bunch of exceptions just to ensure that in the edge cases when maybe you're not executing bytecodes, you can still run the GC. So we hook this in on signal checking and whatnot.
Yes.
But the Eval breaker is basically absorbing all these cases that we need to handle basically the state. And as you will see maybe when we talk about more in depth about the no-GIL work, the no-GIL work also relies on the eval breaker just to do some bookkeeping from time to time and checks that GGC is compact, and all these optimizations that we discussed last time are still working, and we can compactify the memory.
Right, and you also mentioned that this is in ceval.c where Python handles signals.
Yep. So the signals that run on the ceval loop, this is a very interesting behavior, because I don't know if it happened to you as any time, but if you are for instance executing some C extension in Python, let's imagine that you have like this is not the use case of any like big corporation that I work or anything, but imagine that you have a super high efficient C++ framework to do like calls over the network and whatnot, and then you have this wonderful function called run that blocks the thread and it spans a bunch of other threads. So if you execute this thing on the main in the main thread of CPython, and then you suddenly broke Control-C, so you cannot stop the process anymore, because the signals are only checked on ceval.c on the eval breaker, and these signals not only happen on the eval breaker but also only are checked on the main thread. Which means, and there is historical reasons for this, because like some old OSs and before like threads were actually P threads and whatnot, there was some weird semantics. So we force that the signal handlers are checking on the eval breaker, but only if the main thread is the one breaking the eval breaker. Which means that if you are blocking the main thread with some C code or whatever, signals are never processed anymore. Yeah. Which users may not like, and it may need some hacky solutions.
Yeah, it might be a problem.
Those are for the hypothetical poor people that work on financial companies.
We need to invite one to our show.
But yes, like this is an interesting case, and it's very annoying to deal with, because this is not only something that happens in this example that I'm mentioning. This is quite common. If you block for whatever reason the main thread, not really with mutexes, for instance, imagine that you're doing some NumPy calculation, right? So or like tensor multiplication or whatnot. If you're running a lot of C code is not executing bytecode instructions, which means that the eval breaker will never run, which means that signals will never get checked. And this is very annoying, because like if you want to interrupt your long running calculation with Control-C, it will not work. And that's a very bad experience. And that is why there is like a bunch of extra functions that sadly people don't use when they use the C extensions, only the pros, which are called PyR check signals, that you can stick in your C code. If you have a very long loop, for instance in NumPy or TensorFlow, they do this. So from time to time you can manually check for signals, even if you're not in the main thread, or even if you're not executing bytecode. So Control-C still works if you are multiplying NumPy arrays, or you're doing some weird tensor machine learning thing. But this happens on the ceval.c, and this happens on the eval breaker, and that's why sometimes you press Control-C and it doesn't work.
Right. So signal handling is only one of the examples where Python needs to interact with the operating system's APIs and tries to provide an easier model for the user to understand. And one thing that we already mentioned for this is that whenever we had function calls in Python that caused C calls to happen at the same time, even though we theoretically could have an infinite number of Python calls, we couldn't have an infinite number of C calls in the stack. The stack overflow is a real danger, which for a Python program would finish in a very unsatisfactory way, because the entire process would just crash with a very minimal error message, meaning all the users of the Python programming language would have a very hard time understanding what just happened. There would not be a nice traceback. They would not have a way to recover from this error. So for this particular use case, the recursion error, also known as recursion depth exceeded, exception was created, and we were tracking how many times we are recursing, so that if some threshold is exceeded, we would rather stop executing inside the Python interpreter on our own rules and explain what happened to the user with a nice traceback, instead of relying on the operating system to just say, okay, there's no more stack, there's going to be a stack overflow. Interestingly, this implementation detail that started for this particular purpose started being relied upon by Python users for their own algorithmic usage. So if they had some business logic that relied on user input or user data, it wasn't always easy to determine how long this particular piece of code is going to run. So the recursion limit ended up being handy for cases like this. You could even configure how big this limit was. And now that, as I said, we no longer couple a Python function call with a C function call, we could remove this limit. This limit wouldn't be necessary anymore. But it is an API that is relied upon. So now there had to be essentially a re-implementation of this in light of our new advances.
Well, not only that, like you could have, like if you call Python functions for Python functions, you can do this technically arbitrarily, but if you just happen to have any C function in the middle, you will still call new PyEval, eval frame default. So you could imagine this case when, and you know, like all the built-ins are implemented in C, so calling C methods that end calling more Python methods will create this, so you cannot reuse the same call to PyEval frame default, so you can still Stack Overflow with the optimization. If you just call Python to Python all the time, that's fine. But if you have these C calls in the middle, you will still need to call more PyEval frame default because you know you cannot reuse the previous one for a C call. Which means that you know it's still this weird world when you can say, well, I will increase the the recursion limit to 1 million billion to prevent my super JSON to not crash. But still, like if you just happen to run any C function in the middle for whatever reason, you can still segfault. So it's not totally safe. So that's why we still have it.
Right.
But talking about things that are maybe not totally, well, this is totally safe, but it's quite cool as well. In ceval.c, you can have some of the super obscure reasons some very bad code doesn't run slowly. And one of them is this cool optimization that we have. And I don't know, obviously, Gukas, you know it because core developers, we know everything. You're obviously joking. But turns out that, technically, if you add two strings together, or imagine that you have the following case, you have a bunch of words, right, separated, a list of words, and then you want to join them all together. This happens all the time, right? Like you have, you chunk the text in spaces, and then you do some selection of the words, and then you want to join all the words together again into a single string, which is the final text, right? Yes. And many people do this thing when they do for word in words, result plus equal word, right? So they keep adding to the same string.
Yes, they just use plus equal, right?
Right. And this is, as we know, a bad idea because technically this is quadratic. And this is because strings are immutable, which means that every time you add two strings together, you need to allocate a new string, copy the old string into the new one, and add the new one on top of it. Which means that if you add this thing again and again and again, this is going to take O(n) square complexity. But if you run it inside CPython, even if all of what I say is true, you will see that it's not quadratic. Actually, it's more expensive, obviously, than having a list and call join, but this is not quadratic. And the reason is because we have this cool, crazy optimization inside ceval.c, because a lot of people, that are not professional programmers still will write this code, and we can kind of like help them in this case. We have this optimization that basically checks if the temporary that is created by adding the two strings is only like owned by the ceval loop. So basically we check the number of references that we have, and if it's 2 at the time we are receiving it, which is 1 on the variable and 1 in the stack, then we basically reuse the same string, because nobody can really see that we are going to secretly mutate the string. Strings are immutable unless you're a CPython core developer. And so we do this secret mutation, and that's the way we avoid a quadratic algorithm. And this secret lives here. And some people, actually, NumPy developers, I thought, well, this is super cool. Let's do it as well. So I don't know if you know it, but NumPy has this super secret file called temp.elide.c full of monsters. And basically they said, oh, this optimization is super cool because this happens in NumPy quite a lot. Like people are adding NumPy arrays all the time, and they are doing all these crazy binary operations with a bunch of them, so a plus b or something like that. And we want to reuse arrays as well. We like this trick. This will make NumPy much faster. But they have a problem because all this secret thing about checking references in ceval.c is very easy to do if you are writing ceval.c, but it's very hard to do if you are in NumPy. Right. Because they are not inside ceval.c. So this file has these crazy like operations when they like they call backtrace in C and receive a bunch of frame pointers, and they check if this frame pointer belongs to the range that is owned by ceval.c. So they know that whatever is happening on ceval.c, and they do this thing only if the array is very big, because obviously checking the C stack by hand is expensive. So they need to say, well, is this going to be like worth enough? Like maybe not. So maybe let's not do this thing for small arrays. But if the array is very big, that copy is going to be very costly. So there is this like, I don't know, 16 lines if condition, like if a statement just checking all these conditions, which by itself checking is also expensive. So they have factored that thing out as well. It's crazy. This file is ridiculous. And this is just because they want to do the same optimizations, but they don't own ceval.c. So something that is very easy for us is very hard for them.
Yeah, very interesting. So I hope you enjoyed this hour with ceval.c. And if you're scared of the current world we're living in and the world that we are marching towards, like know that you can always go and hug Python 2.6 and the simplicity that we had at the time. But now let's talk about something completely different.
What's going on in CPython?
So over the past 2 weeks, since the last episode, we released Python 3.12.0 Alpha 2. Yeah, with a bunch of new additions to it. So let's start with the obvious question. Is the GIL removed yet? Well, no, not quite, but the process is going very well.
Half of the GIL is gone. It's half.
Yeah, half of it is gone. Like we're going faster than I expected. It's pretty cool to actually see the progress as it goes. So before I mentioned that we are now having instructions for beginning and ending critical sections. So those find already usage inside Python. So functools LRU cache is now protected with the new critical section APIs, and weak refs are as well. So things are moving along. And Sam Gross is now adding new APIs that are necessary for removing the GIL. And one of those is the PyOnceFlag. So something that allows us to ensure that some internals are called exactly once. This is needed for one-time initializations, for example, in the Python AST, and getargs, so APIs for deconstructing argument lists. On top of this, speaking of critical sections, it is now possible to use an @critical-section directive in argument clinic, so the automation that we have inside Python to construct valid parsing of arguments and functions that are implemented in C. So you can use this @critical-section to automate the use of this important API for locking self-objects on methods.
Right. I don't know if it happens to you ever. That certainly happened to me, and I think this is one of the things that every core developer at some point finds, that there is some sneaky secret APIs that when you call them, they don't give you new references. And this is like quite important because, like when you're calling some APIs, normally in CPython, like by list new, you get a new list and then you are in charge of it. You are the owner. You need to dereference the list when you finish. But there is some APIs that sneakily return you a reference that you don't really own. One of them, I think the most common one, is PyDigGetItem. So this is the API to get an item from a dictionary, given the key, but that you don't own the reference that it returns. It's borrow, which is like, you could argue there's an optimization because you don't need to the reference the object that you get. Only if you wanted to encrypt the thing. But this is a problem with the new world we live in, because in no-GIL, weak references, which is what these kind of references are. Borrow reference, not weak reference. Borrow reference, which are these references, are quite dangerous because it's very difficult to reason about them with threads, and it's very easy to get one of these and then another thread just removes the reference, and then you have like garbage. So Victor Stinner, which is doing a lot of like work around this the C API, added a new function called PyDigGetItemRef, which is doing the same thing as PyD get item, but it will return you a strong references. And this is quite important because like without these APIs, new C extensions that need to deal with the GIL, and internally, it's very difficult to distinguish in which case you are supposed to like take it because it's risky, and in which case you're not. And in general, in the presence of free threading, you will always want APIs that return strong references, just to avoid this case when you need to do special things just because the API returns you a borrow.
Right, and this is a very cool API because it not only handles the strong reference use case correctly, but to do this, it handles also the case when a key wasn't found in the dictionary or some other error happened. And it turns out that almost every time that we were accessing a dictionary and looking for some key in the C API and the internals of Python, we had to by hand handle those three cases. So the code for this was just every time a little different, but trying to do the same thing. So Serhii Storchaka went on a spree to replace all those old APIs with the new variant. And you can like actually follow this issue, find it on our issue tracker, where it's mostly just red PRs. Like the changes end up being much shorter with this new elegant function, pydict get item ref. Very cool, very cool.
Red PRs as PRs that implement, like remove lines, more lines than they add, right?
Yes, exactly.
It's not like dangerous PRs or anything, right? Red PRs.
So Victor, in fact, started 3.13 with just removing a bunch of private things from the C API that were never intended to be used by external users of Python. But every time there is some function that is convenient and already there, people will use it. So a bunch of users of those removed functions complained that there were no valid equivalents available in the existing API. So Victor added, for example, pylist extend, pylist clear, and pydict pop. So APIs that are equivalents of private APIs that were removed in the meantime.
Well, one thing that I'm quite happy to also report is that I merged a PR that had 2 years already sitting there, like, getting marinated or something. And this PR was basically implementing better error messages for not matching elifs and else statements. So you have you're writing a complicated if, elif, else statement, and then you have one of them, the two of these that are not matching. And the reason this PR was sitting there is that unfortunately we do want our contributors to actually do the work. So even if it's very easy for us to just jump there and say like, I'm going to just fix all these problems, the idea of contributing is that you have a great experience because you make your change, but also you learn how to do these things. And sometimes, unfortunately, this iteration of like us telling the contributor, oh, you forgot to run this command that maybe you didn't know that you needed to run, or the reason you're seeing this error is because of this. This quite take a long time because, we take a long time to answer, and they take a long time to answer because everybody has life outside CPython.
Sure.
And unfortunately, this is one of these cases that I'm a bit embarrassed that took 2 years. But in Python 3.13, we will have better error messages for this case.
No, very cool. Like some of those things need time to bake. Like very often there are open issues about things being suboptimal, but it's not very clear what you should be doing in the first place. One that case was fnmatch.translate. So this functionality that we had that allowed you to translate shell wildcards into regular expressions. And it was already there, but it had this very weird behavior when the asterisk would actually go through path separators. So it would catch the entire path, across the path separators. So that was useless for what most people wanted translate to be, but it wasn't clear how to solve this.
Right.
So now, finally, Barney Gale added a function to the glob module that does this translation in a more predictable way. So now it's easier to use correctly without this big gotcha. And in fact, the reason he did this in the first place is he and Alex Waygod way into pathlib and started optimizing things that pathlib was doing in inefficient ways or non-efficient ways. So now there are plenty of smaller optimizations in pathlib that ultimately make it way snappier in Python 3.13. So for example, just this glob.translate is speeding up directory walking by 20%. So it should be a big difference for any sort of scripts that hit the file system written in Python, running on Python 3.13.
That's super cool, actually, and those users will certainly notice 20% on those functions. By the way, speaking of all bugs that got fixed, one of the cool things that we have now is that TLS-PSK, which, it could be anything unless you are into security and web protocols and whatnot. This stands for pre-share key because, security people like to put acronyms without vowels. So this is now supported in the SSL module. Just to be clear, normally certificate-based authentication should be preferred, obviously, always this. But this is quite an interesting protocol because normally it's very common on web stuff. But that turns out that it's quite common on embedded environments that want their communication not to be clear text. So, now this is supported on the SSL module, so they can use it, which is, maybe it's not going to bother everyone, but it's quite cool.
Right. Obviously, pre-sharing the key is the tricky bit, but what you get for this is way cheaper communication, right? Like with not having certificates and this entire handshake at the start of your communication, for example, is important when you're running on battery and you have environments where you cannot charge your battery very often. So for this particular use case, we were always relying on third-party libraries. Now the built-in SSL module finally supports this. So that's great to see. And the idle debugger also got some love recently. Anthony Shaw increased the test coverage of that debugger in idle from 19% to 66%.
Wow.
And while doing this, he squashed quite a few bugs. So that was awesome to see. And similarly, pystats, PY, so the module that can actually display what you gathered using cprofile, that coverage was bumped by 1%, so it doesn't sound like much. But sometimes those small wins are quite non-trivial because they touch on exceptions being raised or other edge cases that aren't very easy to model in a test case. So all of those improvements in test coverage are very good to see. Like every time we're gonna have those small improvements, it's going to find some issue or prevent an issue in the future. I remember when I first started fighting for 100% line coverage for config parser, some of the other core developers were kind of skeptical of whether it's worthwhile spending this time on, which is essentially a bunch of uncovered except statements. And what turned out was hiding there were 3 or 4, I don't remember anymore, but it was either 3 or 4 bugs just on this one last percent of coverage not covered, because those were the tricky bits.
Exactly.
And it turned out that they were raising the wrong exception or they were returning something entirely incorrect on just some particular error case and so on and so on. So all of those are still in the test case. You can look for them, and the test case for this is literally called just, I think, coverage 100 or something, because those were just like random variety tests that were just there to make sure that we hit all of those metrics, but it was worth it. So that was very interesting.
Well, those are all the cases where people are like pragma no cover, because this is super difficult to test, and it's every time something weird happens is that thing. So everyone that removes one of those weird pragma no covers and adds trace crazy shit happened, you are in my heart.
Exactly.
And I think the other exciting thing that we already mentioned is that we have our first micro op in the tier 2 interpreter, which is for iter. So in the future, if you are in some Python and then there is this trivia section when you can gain awesome prizes, and someone asks you, what was the first micro op that appeared in CPython? Now it was for iter. Well, maybe we removed it for 3.13, so all of this is wrong. So, and then you lose, but we'll see.
Yes, everything is still in the air. I do hope that this wasn't too scary for an episode. My hope here was to demystify the core of the interpreter just a bit and show you what it means to interpret code. This is an area of active development, which is why we are talking about it constantly. And this is some of the most fragile pieces of Python. Even a small bug in the central place makes the entire interpreter explode, essentially. So we need to be very careful to make changes there. But inside that complexity of today's ceval.c still lies this very elegant architecture that I found when I first looked at this file back in Python 2 days. And since this still lives in the repository on GitHub, you can do this as well. You can look at it and understand what drives the programming language that we are using.
And maybe now, after listening to this episode, you can finally know why all these cool people keep saying the CPython VM. And you say, but what is this? This is not a VM. Now you know.
Wait until you find the abstract base class called container.
No way.
See you next time.
See you next time.